Exponential functions. These are very popular. Something that grows exponentially is something that grows like the following way. If you're talking about germs, viruses, animals, they double. Their population doubles, triples, quadruples. When you hear that type of talk, that means that behavior is exponential. This is the equation. Now, notice the shape of the graph. The graph can be rising, that would be growth, or falling, that would be decay. Also, notice there's a horizontal asymptote. So exponential functions already come packaged with a horizontal asymptote. Notice they're telling us that the a cannot equal 0, because if it did, all of this would go to 0, and it would be y equals 0, which would be a horizontal line. It wouldn't be an exponential anymore. And then look at the b. If the b could be between 0 and 1, and the b can be greater than 1. If the b is greater than 1, then you expect the graph to be rising. If the b is between 0 and 1, which means a proper fraction, if the b was like a proper fraction, like a 1/2, 2/3, then you expect the graph to be falling. For example, this is y equal x, 5 to the x. The b is greater than 1. The b is at 5. So you expect the graph, before you even graph it, you expect it to look like this. It's rising. Look at this one. This is 1/5 to the x. So 1/5 is between 0 and 1. So you expect this one to be falling. But be careful. The 1/5 can also be written as 5 to the negative x. So another way to know that the graph is falling is that you have a negative exponent. But if you have a negative exponent, make sure you check it to see if, when you take the reciprocal, because the negative exponent means takes the reciprocal, 5 over 1 becomes 1 over 5. Make sure the b is between 0 and 1. For application problems, the a is going to be the original amount. It could be the original amount in a bank account. It could be the original amount of some population of some animal, anything that grows. That would be the original amount. Now let's look at the domain and the range. Remember, the domain are the x's that are being used, the inputs are the x's that are being used to produce this picture. So notice this graph is on top of all the x's. So these arrows go forever in that direction, goes forever in this direction, tilting this way. So all the x's are being used, so all x's are okay. They're in the domain from negative infinity to positive infinity. Look at the range. There's a horizontal asymptote, so the graph can only be above y equals 0. So anywhere y is greater than 0, you'll find a graph. Now, a clarification. This is an exponent, and this is an exponent. But when the exponent is a constant, a number, you don't say it's an exponential function. You say it's a power function. When the exponent is a variable, that's the only time you say it's an exponential function. Here's a problem. The annual amount of wine in millions of gallons consumed in the United States can be approximated by this equation. So anytime they give you a formula or an equation, find out what the letters are going to mean in the problem. So notice the annual amount of wine consumed. So that would be this part. This is like your y. This is the amount of wine, the f of x, which is like a y. Where x equals 50 corresponds to the year 1950. So the x is going to be time. So this is amount of wine, f of x, and x, all by itself, x will be a time variable. How much wine was consumed in 1990? So they gave us some information about wine consumed in 1950, and they want us to give them the answer for how much wine was consumed in 1990. They told us that 1950 is going to correspond to x equal 5. So what would 1990 correspond to? Well, just add from 50 to 90 at 40 years, and that makes x equal 90 because time is running. So now we know that for the x, we're going to replace it with the 90. So we could know how much wine was consumed in 1990. So you substituted, key this in, and it turns out to be 462 million gallons of wine were consumed in 1990.